Hey, A-level physicists, what's the crack? So today what we're doing is we're going to learn a bit about resonance. Okay, so a lot of words normally come up in these questions for these. I would recommend drawing pictures again. Okay, so what it says is a ship moves through continuous waves at this velocity of the water, and the ship is moving at 8. So what I would draw is draw my little picture. I know the water, it's telling me, is moving at 14.2 meters per second, and it's telling me the ship is moving at a speed of 8 meters per second. And it says it's going to be relative to the seabed. So then your seabed is down here. So your water is moving at 14.2 meters per second to the left, and your ship is also moving at 8 meters per second to the left relative to the seafloor. Okay? So what it says is the natural frequency of this ship is 0.13 hertz. Okay? And it says that on the ship, someone is going to have an operation. And in order for the operation to happen, the ship needs to be steady. So we need to figure out, do we tell the captain to stop and anchor the ship, or do we keep the ship moving at the 8 meters per second? Okay. So anytime you see a question about the heave oscillations or natural frequency, you need to be thinking about resonance. Okay, and I know resonance is when the amplitude of the oscillations greatly increases. So let's say I've got an atom vibrating. If I hit resonance, that atom is going to vibrate with a much greater amplitude. Okay, so clearly I don't want this ship to hit resonance because this would be really unsteady. So I need to figure out what are the two frequencies. Okay, so the question I know for frequency and speed is C equals F lambda. Okay, but instead of using speed of light, we're going to use V because we're kind of figure out what the velocity is. So the velocity is the frequency times the wavelength. So we'll look at the condition first if they stop. Okay, so if the ship anchors itself, it's completely stopped. That means what's moving relative to it is the speed of the water. So what I'm going to use is the speed of the water. So it's 14.2 meters per second. It's going to equal some frequency times by the wavelength. The wavelength is a distance measured in meters. So I look back in the question and I can see that up here. So the wavelength I'm using is 118. So to find the frequency, I just divide both of these numbers by 118 and I get a final answer of 0.12 hertz. So before I do any more math, I can see that those are quite similar numbers. It's probably not a good idea to anchor it because then the boat will move loosely with the water. Okay. If you look at the other extreme, again, V equals F lambda, the speed now, if we just keep moving, if I'm on the boat, I don't actually think that I'm moving at 8 meters per second because if I'm on the boat and the water is moving beneath me at 14.2 meters per second, I see both of them moving. So for me, I'm actually moving at 14.2 minus 8 meters per second. Okay, so the speed is 14.2 minus 8 equals the frequency times 118. So when I subtract these numbers and divide by 118, the frequency I get here is 0.05 hertz. Okay, so again, just to summarize, we don't want resonance to happen because if resonance happens, the man will be able to do his operation. So if I have the boat anchored, so the boat is just moving with the water, the frequency is going to be 0.12. That's the applied frequency. And because that's so similar to the natural frequency, I will get resonance. The amplitude of the oscillations will greatly increase. So what we want him to do is that we want him just to keep moving at the 8 meters per second because then the frequency, the applied frequency, is very different from the natural frequency. So I won't get resonance. And that's grand.